Alright, so this is going to be a video on ionic bonding. This video is going to explain what ionic bonding is, how ionic bonding works, and how ionic compounds are named. Atoms are a lot like people. They try to be as stable as they possibly can. Some atoms, like noble gases, are as stable as they can be, just being their own separate atom. Other atoms, like oxygen, are more stable when they're grouped up with other atoms. Some atoms are more stable getting rid of some of their negative charges, while others are more willing to take on a little negativity to become more stable themselves. When it comes down to it, atoms, like people, just want to be stable. The great thing about atoms compared to people is that they're a lot easier to understand in terms of matching up with other atoms than humans are with matching up with other humans. Pretty much every substance we see is composed of atoms being bonded together. Besides the noble gases, all other substances are made with atoms that are bonded together or could be bonded together. This includes things such as the oxygen we breathe in, the CO2 that we breathe out, the water we drink, and the salt that you add to your food. There are two types of chemical bonding, ionic and covalent. Ionic bonding, as you may have guessed, based on the name, involves the bonding of ions. Covalent bonding involves the sharing of valence electrons. The prefix co means together, and the suffix valent means related to the valence electrons. This will be talked about more in the next video. Showing how atoms bond is extremely easy using Lewis structures, so make sure you've mastered how to make those before watching the rest of this video. Before we start, it might be a good idea to introduce some vocabulary first. A compound is when two or more elements bond together chemically. Ionic compounds are formed from ionic bonding, and molecular compounds are formed from covalent bonding. As discussed in a previous video, metals tend to lose their valence electrons to have a filled valence shell. Non-metals, on the other hand, tend to gain electrons to have a filled valence shell. This principle is what causes ionic bonding to occur between metals and non-metals. So we're going to go over an example of this that will help explain this concept a little more. Here's a sodium atom and a chlorine atom. Both atoms want to have a filled valence electron shell. Sodium, having one valence electron, will lose that electron, which chlorine is more than willing to gain. This causes sodium to then have a positive charge and chlorine to have a negative charge. Note, both atoms have filled valence shells now. These opposite charges attract each other through electrostatic force to form the compound sodium chloride, or NaCl. Here's a video of sodium being reacted with chlorine gas. As you can see, energy is given off due to both the sodium and chlorine becoming more stable. The end result is salt. It is important to know that these positive and negative ions of sodium and chlorine also attract neighboring sodium and chlorine atoms to form a crystal lattice structure illustrated here. This is why salt and other ionic compounds form crystalline structures. Other interesting characteristics of ionic compounds is that most of them dissolve in water into their respective ions. These ions can then be used to conduct electricity. Because the ions in ionic compounds all attract each other, they are also all solid, have high melting points and boiling points. Let's look at another example. Let's see how aluminum would react with oxygen. The aluminum is willing to give up its 3 valence electrons to have a filled shell. Oxygen is willing to gain 2 of those electrons to have a filled valence shell. Aluminum still has that 1 valence electron that it wants to lose. It is important to know that atoms do not exist by themselves. There are billions and billions of atoms in a sample of aluminum and a sample of oxygen, depending on how much you have. That last valence electron will be lost from the aluminum and gained by another oxygen atom. Now the aluminum has a filled valence shell. The problem now is that the oxygen that gained that valence electron still needs another electron to have a filled valence shell. As we said, there's billions and billions of other atoms, so there is going to be another aluminum atom right next to that oxygen that's willing to give up another one of its valence electrons. It does so, but then it still has 2 more valence electrons that it wants to get rid of. Another neighboring oxygen atom gladly takes 2 of those electrons, and then every atom in the formula unit has a filled valence shell. This represents the final chemical formula of an ionic compound formed between aluminum and oxygen. The formula would be Al2O3, which you would say is aluminum oxide. The resulting crystal ends up forming sapphire, shown here. Another way that you can look at how ions bond would be to look at their charges. In order for those charges to balance each other out, you would need 3 oxygen ions for every 2 aluminum ions. This would make the formula the same with that Al2O3. The naming or nomenclature of ionic compounds is as follows. The name of the metal is the first word of the ionic compound's name. The second word is the nonmetal with an "ide" added to the end. The suffix of the element is basically replaced with IDE. Some metals can have different charges. For example, iron ions can either have a +2 or a +3 charge. Whenever a metal is used that has a variable charge like this, the rules for naming change slightly. The first word is still the metal name. The difference is that the charge of the metal is then written as a Roman numeral in parentheses right after that metal name. The second word is then the nonmetal with the "ide" suffix. Let's look at some examples to cement our understanding. These all have metals with fixed charges. They would simply be read as sodium chloride, magnesium fluoride, aluminum carbide, and calcium phosphide. All of these ionic compounds have metals with variable charges. They would be read as iron 2 chloride, copper 1 fluoride, iron 3 oxide, lead 4 chloride, and manganese 4 oxide. So you might be thinking, who cares about ionic compounds? Well, besides the general understanding of creating metals that rust less that can be used in automobiles and other machinery, knowledge of ionic compounds also helps with producing household items. Examples such as iodized salt. Iodide ion is vital for proper functioning of the thyroid gland, among other things in the body. And because our diets rarely have iodide in them, iodized salt can help you get the iodide ion that your body needs. The iodide ion is bonding with potassium to form potassium iodide, which is the main ingredient in iodized salt. Furthermore, the essential minerals that are in vitamins are not actually in metallic form. For example, you need such things as copper and iron and manganese and magnesium and that sort of thing for your body. Those metals don't actually come in pure metallic form. They come in the form of ionic compounds. Toothpaste's main ingredient is sodium fluoride. The fluoride helps strengthen the enamel in your teeth that leads to less tooth decay. Disinfecting wipes have ammonium chloride in it, and clog remover has sodium hydroxide in it. These are just a handful of many other examples of ionic compounds that you deal with on an everyday basis. So that's ionic bonding. If you have any questions about anything in this video, let me know.